All right, today we're going to tackle a concept from chemistry that you hear about all the time, pH. I mean, what is it that makes lemon juice so sour or soap feels slippery and basic? Let's dive in and really break down the science. We throw these words around all the time, right? Acidic, basic. But what's really going on at the microscopic chemical level to give things these properties? That's the big question we're going to answer right now. First things first, we've got to get a handle on our main tool here, the pH value. So what in the world is it? Okay, so at its core, the idea is actually pretty simple. The pH value is just a scale, a ruler, if you will, that tells us exactly where a solution sits on that spectrum from acidic to basic. It's kind of like the language chemists use to talk about this super important chemical property. But what actually decides that number on the scale? Well, it all boils down to this epic battle between two super tiny but incredibly important particles. So let's meet our key players. All right, picture a chemical seesaw. On one side, you've got hydrogen ions, or H+, and on the other side, you've got hydroxide ions, OH-, and it's all about the balance. The more H+ ions you have, the more acidic the solution gets, which, and this is a key point, means a lower pH value. On the flip side, the more OH- ions you pile on, the more basic it becomes, pushing the pH value higher. It's all about which ion is winning. Okay, so we've met our ions. Now let's put them on the map, the pH scale, to see what those numbers actually look like in practice. The pH scale really lays it all out for us. Right smack in the middle, at a pH of exactly 7, you've got neutral stuff, like pure water. It's perfectly balanced. Now, as you go down the scale, towards 0, things get more and more acidic. And when you get to anything below a pH of 2, well, that's what we call a strong acid. And what makes it strong? It just means it's incredibly good at dumping its H+ ions into the solution. Now, if we go the other way, up from 7, solutions get more basic. Anything over a pH of 12 is considered a strong base for the exact same reason. It's just a pro at releasing those OH- ions. So we've got our two champions, right? Acids with their H+ ions and bases with their OH- ions. So what happens when you put them in the same ring together? Well, get ready because this is the main event. It's called neutralization. So neutralization is the official name for this chemical showdown. It's what happens when an acid and a base meet. And just like the name says, they basically cancel each other out. So how does this actually happen? Well, it's like a really simple 3-step dance. Step 1, you mix the acid and the base. Step 2, our star players, the H+ from the acid and the OH- from the base, spot each other across the crowded room. And for the finale, step 3, they combine. And they form a brand new super stable molecule, H2O. You know it? It's just water. Okay, the theory is great and all, but to really get it, you've got to see these ions in action. So let's walk through a super clear, detailed example of a reaction. So for our example, we're going to mix hydrobromic acid with a base called sodium hydroxide. Let's really zoom in and see what's happening on that ionic level. The moment we mix these two, the solution is suddenly filled with 4 different kinds of ions. From the acid, we get our hydrogen, H+, and bromide, Br-, and from the base, we get sodium, Na+, and of course, hydroxide, OH-. Right now, they're all just kind of swimming around in a beaker, but not for long. And this is the moment it all happens. Out of all those ions, the H+ from the acid and the OH- from the base are like magnetically drawn to each other. They slam together, and poof, they're gone. In their place is a stable molecule of water. This single reaction is the heart and soul of neutralization. All right, so the main event is over. What's left in the beaker? Well, we've got our brand new water molecule for sure, but what about the other guys? The sodium and the bromide? They're still just floating around. They didn't actually do anything. They were basically just spectators watching the main event. Okay, now listen up, because this is a super important rule. For a perfect neutralization, you have to add the exact right amount of acid and base so that every single H+ ion finds an OH- partner. If you nail it, there won't be a single leftover H+ or OH-. All you'll have is water and those spectator ions. All right, so let's do a quick recap of the big takeaways. First, pH is our ruler for measuring acidity and basicity. Low pH means lots of H+ ions. That's acidic. High pH means lots of OH- ions. That's basic. And when you mix them,
The H plus and OH minus team up to form water. That's neutralization. It's simple, it's elegant, and it's a really powerful idea in chemistry.
But wait a second. This leaves us with one last really interesting question. We know the H plus and OH minus make water, but what about those spectators we mentioned, the sodium and the bromide ions? They don't just vanish into thin air, do they? Nope. They find each other and form something you almost definitely have in your kitchen right now, a salt. And how that all works? Well, that's a story for another time.